Okay, we're gonna see how this goes. I forgot my iPad, and you guys already know my chances of screwing that up is really high. So now we're going the old-fashioned way. Um, so over under of technical difficulties, we're gonna set it at 2.5, and we can start the betting on the side if you want. Well, hey everybody, I hope everyone is doing good. Thank you for being flexible on Monday. Um, I did post that video. If you haven't gotten a chance to review it, please do so. That we will have the quiz posted after class that has the recap of the elastic settlement. And then today we're going to be looking at an empirical way of calculating elastic settlement. Second best last name there, Schmertman. His technique, which is a really cool and helpful technique. And then today we're also going to be getting into shear strength, and the next topic there. So yeah, really important to still watch that video over there. So where we're at today, we have a quiz that will be posted shortly after class. I still just need to make sure everything is covered correctly on it. And that will be due this Friday. And then your homework 1 has been posted. It's due this Sunday, I believe. Yeah, this Sunday. It's mainly going to be on consolidation and settlement. So it will not be on the shear strength stuff that we are talking about today, but your quiz will be. So please make sure to keep in mind with that. Okay, another fun little opportunity if anyone is interested. A lot of info here, and Chris can double check on this. But we got reached out by JEA. JEA, which if you guys don't already pay so much money in utility bills and stuff, you will soon whenever you have to rent or buy a house here in Jacksonville. But they do a lot of engineering, a lot of civil engineering, as well as structural engineering and energy kind of sector. And they're looking to hire as soon as possible a position in the structural engineering realm. And it's kind of cool because they're working primarily on updating and maintaining the existing power stations, the structural components of it, and as well as a new nuclear reactor in Vogel over in South Georgia that they're currently constructing. So you get a little chance to work with structural steel design for existing as well as new kind of unique niche structures. So if you're interested at all in structural engineering, they reached out, seemed pretty urgent. You'd be working under a structural engineer who has a lot of experience in kind of like taking you under the wing. It's titled associate engineer, which is kind of cool too, but they're looking for entry level. So you kind of get a chance to start one leg ahead in the industry by being titled an associate engineer. So I put the 2 contact informations, the link as well. I'll also post it in a Canvas announcement. But if you are interested and want me to get you in contact with any of these 2 people just to share more information, I'd be happy to do so. So let me know. Or you could talk to Chris because he used to work with them too. All right. So after today, we are going to be talking about immediate settlement or elastic settlement in sands. And then also we're going to be introducing shear strength of soil. And shear strength of soil is one of the most important concepts of foundation design, especially introducing bearing capacity. So when we talk about shear strength of soil, I want you to think like, okay, for concrete, we have compressive strength. For steel, we have like bending moments and tensile strength. For soil, we have shear strength. That's like the important thing that we design against. The Schmertman method too. Schmertman method too. Let me go to a pen. This is a cool one because this is an empirical technique. So if you remember, or if you haven't watched the lecture yet from Monday, those methods like the Bowles methods and all the elastic settlement methods, that's based strictly off of the theory of elasticity. So that's strictly theoretical, like same kind of with Boussinesq and all of those things where we talked about the delta sigma z, the increase of strength. And that's good to a certain extent, but really like the heart of geotechnical engineering and foundation design is empirical. And empirical is using real data to set functions and statistics to then use to predict. So it's data trained rather than theoretical is just based off of a bunch of assumptions and like the math side of behind it. Now there's room for both in geotechnical engineering, but like we're leaning towards a lot of empirical based things. The other cool thing about Schmertman was he's a professor at UF and still lives in Gainesville. So his methods were actually developed using Florida soils and Florida sand. So it's really commonly used here in Florida, and it is empirical, not theoretical, like we see in the previous slides. So has some added benefit. It's a little bit more easily implemented to subsurface testing, specifically the cone penetration test, which we'll talk about in more details today. So if you're interested, these are the resources, the immediate settlement. If I find any of the FDOT reports discussing the Schmertman method, then I will also post that. But he's a professor very well known in the space, even though he's a professor here in Florida. He's also in both of these textbooks, so you'll be able to find these techniques in the textbooks as well. All right, John Schmertman, our boy, 1978. He developed this technique using strain influence. And this is an empirical method. And also, as I'd said, it's developed using Florida sand, so which is kind of nice. It's specific to our geologic formation, but it is also applicable in other types of sands as well. But it is nice to know it's a little hometown development here. So the equation looks a little bit different, but still some similarities in all of from the previous Bowles techniques and the other elastic settlement techniques. With any geotech, especially especially empirically based, we're going to have a bunch of coefficients. And then the main thing we have here is this is based off of the layers underneath our soil. So that's why we have that big sigma. The big sigma is just the summation of all of these different layers. We have these correction factors right here, C1 and C2. C1 is a correction factor for the depth of foundation. And then C2 is a correction factor to account for creep in soil. This is the time dependent. And so you can see that function, it's time in years. So the longer time that we are considering, then the higher this coefficient is. But most of these coefficients are going to be less than or around 1. Like they're not going to be changing the entire settlement too much. So yeah, these are coefficients. And then right here, these Qs, although this is a weird way of showing it, these Qs are just the effective stresses. So very similar to the sigma that we've been talking about, the effective stress, the sigma prime. But instead they just used Qs for some reason. I don't know why they decided to use that in other ways or not. So this is still a elastic settlement. So you can still see the function or the soil property that we care about is the modulus of elasticity of soil. But you'll see there's good correlations to subsurface testing for this modulus of elasticity, which helps us get a understanding of the modulus of elasticity, how it changes with depth. So we can do a standard penetration test, or we can do a cone penetration test, and we can correlate that testing data, which is, a resistance value per depth of penetration or depth of soil. We can get that and then correlate it to ES. So let's focus on the influence factor. That's going to be the hardest thing to find because this is going to be site dependent. Our Q bar is the stress from the foundation. So that's the structural loading divided by the area. So the structural load of our footing, or sorry, the structural load of the column or whatever divided by the area of the footing. And then our effective stress at the base of the foundation, that's our gamma times our depth of footing. And I'll show it and illustrate it on the next slide here. All right, so for the influence, the strain influence, the trickiest part of this is that the influence is going to change based off of the footing type. Now, hopefully this makes sense. When we're talking about influence, we're talking about the depth at which the soil is affected due to the foundation. So obviously, like if we were super down, like 100 feet below the level of the footing, and we apply some load on the surface, the stress is going to be distributed through the soil that something at 100 foot in depth might not feel the weight of that soil, right? It's so right directly underneath the soil, we're going to have a pretty significant amount of influence. But as we go further in depth away from our footing and away from the load, we're going to see a lower and lower influence. Hopefully this makes sense, because when we were talking about the 2-to-1 method or any of the delta sigma z's methods, like the Boussinesq method, like this is kind of the same case. As we go further away from the source, the stress dissipates and we feel less and less of it. So that's what these profiles are saying, basically. They both start at the depth of footing, which is important to note here. So the influence obviously starts at the depth of footing. So this is the ground surface up here. And then dependent on the depth of footing, that's obviously where the influence or the increase of stress is going to occur. But what Schmertmann assumed was that it follows this kind of, I don't know, trapezoidal rhombus shape or whatever. So it's going to have a starting point at either 0.1 or 0.2. It's going to increase to a depth of, or a value of IZ, which is the maximum influence. And this is going to occur in two cases, at a depth of Z1 or B, if we are talking about a strip footing. I'm just going to put a dashed line here just to distinguish between these two. Uh-oh. Do it. Wait. Okay, we're still good. Or at a depth of 0.5 times the base if we're talking about a square. So this is the influence profile for a square footing. And then this is the influence profile for a strip footing. Now, there's also an influence profile for a rectangular footing, but we're just going to focus on square and strip in between. You can see those are the two maximum extents here. I should note too, for the square, this is also used for the circular footing too. If you have a circular footing, the same thing. So that's where our peak influence is going to occur with depth. And then what also we see is for a strip footing, we are going to have zero influence of our footing at a depth of, at a depth of 4 times the base. If it's a strip footing, if it's a square footing, then we're going to say if we have we will have zero influence of our footing at a depth of 2 times the base. So remember, for the square footing, it's a base is times length. For the strip footing, the base is always the shorter of the two. So length is always the longer geometric function there. So the starting point is important, 0.1 and 0.2, that's our influence factor. And then the max is also important, and the depth at which it occurs. And the max is a function of this right here. This is how we calculate this max influence number. So I'm just going to put a little star here. That's the star. To find that star value, we'd calculate this. Where our Q bar is the same on the previous page. It is our stress at our footing. So this would be the column load divided by the area of the footing. And then our Q, technically this is Q prime. This is our effective stress right here. So our unit weight minus our depth of footing, or sorry, times our depth of footing. So the effective stress at that depth of footing. And then the Q prime Z1 in the denominator, this is the effective stress at a depth of Z1 before construction of the foundation. So this is important because this is assuming, or sorry, not assuming, using the ground surface elevation, so GSE. So this is not accounting for the depth of footing taking out any construction. It's before construction of the foundation. So this is our in situ effective stress. So that's this one. So that's again why that was one of the important parameters that we needed to learn in total stress and pore water pressure, is because it's used here. So that's that QZ1, which is way to do this. Uh-oh. There we go. Now we're talking. Okay, sorry. So this value here is this. Either this or this. I know that might be hard to see. It's a little blurry. So that's the two values right there. So the other thing I should note too is if you're using a circle, then B is just equal to the diameter. So the diameter of the circle. So what we do is we use this influence profile to determine this last part of our settlement equation. So this sigma IZ over ES. So this is shown in this example here, and I'm going to go through these steps, and then we'll go over a real example as well. But first, what we want to do is we want to plot the foundation and the variation of IZ with depth, and we want to do this to scale. So we would have our depth of footing, and then that is where we have our profile starting. And you can see it will show that profile there with the Z1 that we calculate based off of the loading, and then also the profile of our triangular or trapezoidal profile based off of whatever our type of footing is. And then of course, like if we're in just a single homogeneous soil layer, then that's great. Like we only have one layer to add, and that's super nice. But most of the time we're going to have the stratified sands or stratified soil layers where we have to determine the average ES or the average Young's modulus like in each one of these layers. So this is where the correlations come in, and we'll talk about it here in a second. A very common one, if we're using CPT, or who remembers, what does CPT stand for? Type of test. Yeah, the cone penetration test. Yeah. The two major types of subsurface testing is standard penetration test, which is the hammer that like hammers the drill bit into the ground, or the split spoon sampler. And then you have the cone penetration test, which is like the surgeon's version of it, where it hydraulically pushes a 2 centimeter probe into the ground. So instead of having dynamic like measurements, you have a nice smooth profile. So for this cone penetration test, typically what we use is this ES profile of about 2.5 times the QC, which is the cone tip resistance. Or there's other direct measurements from the standard penetration test that we'll go over here in a second. But this would be the whole thing. You'd have the ES, you'd have the Young's modulus as a function of depth, and then you'd have to stratify, or, you know, it's going to look like this blue line shown here. You kind of understand how to find this average profile to set your different layers. So in this example here, we're going to have a layer 1, layer 2, 3, 4, and 5 separate sand layers, which means this sum here would consist of 5 calculations. I don't know how to write this. Summations. So you'd sum up 5 things for each individual layer. So that delta sigma z, and it's kind of shown here, that delta sigma, or sorry, that delta z, not delta sigma. I say that way too often. So that delta z is the thickness of each individual layer. The IZ is the average influence value in that layer. And then the ES is that averaged Young's modulus, whatever you set there for it. So the easiest way to do this is to use some type of Excel or some type of plotting software, because you need to find this average value here, which is the middle part of the triangle. So the IZ is at the middle of each layer based off of the influence. And we'll go through an example of that there. So once we add each respective term here, we can calculate the remainder of the equation for the SE. So that's what that summation is. So the hardest parts for this is first making sure your profile is correct for your influence. And then also the tricky part can be determining this ES, this material or this soil property with depth. So let's look at some of the most common types of correlations. So correlations from subsurface testing for Young's modulus. So for sandy soils, which is what we're going to be determining here for settlement, because it's elastic settlement, we use a generalized function as follows. Hopefully hopefully this color works. So we see that the Young's modulus divided by PA, which is the atmospheric pressure, is equal to some correction coefficient that we're going to call alpha times the N60 value. So if you remember, N60, this is the SPT N value corrected for 60% energy. So it's a normalized value. And so we went through a whole process. It's based off of in our Geotech 1. So go back and look through those notes in your Geo 1 class. Or you can look up ways to calculate the N60 value. It's based off of the drill depth. It's based off of the diameter. It's a normalization technique for N60. An N value, remember, that's the number of blows it takes to go 1 foot or the last 2 6-inch segments of our drilling per layer. So our SPT, the sampler, has 2 feet, or I mean, it's a little bit longer. It's 2.5 feet. We do 18 inches of hammer hits, and then the last 2 6-inch segments, so the last 12 inches, we count the number of blows to go that direction or that length, and then that is our N value. So our PA this is our atmospheric pressure. Make sure we check the correct units, because this needs to be in the same units as, what we hope the ES is, whatever our ES is going to be. So let's look at the alpha values. So alpha, this is a kind of a generalized rule of thumb. Our alpha is going to be equal to 5 if we have primarily sand with some or minimal fines. Our alpha value is going to be equal to 10 if we have what we call clean sand, meaning no fines. And that this is also normally consolidated sands. And this is a hard like thing to think of because we don't do a consolidation test on sands. So basically what we're doing is just thinking about like the geology of the region, being like, okay, was this sand, did it used to have like a lot of weight on top of it? You know, it's kind of more assumed. It's not as like tested. We don't do consolidation tests. We don't find pre-consolidation pressure of sands, all that stuff. Um, and then here, this would be again for clean sand. So with no fines, but this is if over consolidated issue. So what do you think is most common in Florida out of all those three? Five. Yeah, this is also a range, so you can use stuff in between. Like you can see like the more over consolidated, the more like clean we get of sand wise, like low fines, then that higher that alpha value is. So yeah, most of our sand in Florida is going to be normally consolidated because it's recently deposited, like by beach sediment. Only in some areas in Gainesville and up in the like Ocala, the center, the ridge areas, do you see like maybe slightly over consolidated sand. But most of it will be between that alpha 5 or maybe sometimes alpha like 7 in between, like if you're using that for Florida. And then of course, atmospheric pressure here most of the time will either be 2,000 pounds per square foot or 100 kPa here at like atmospheric pressure. But in case you ever do geotech work up in like the mountains or something, it might be a little different. Okay, so that's commonly used, or again, this is commonly used for SBT. SBT, you always have to be a little careful, especially because you know we're have to correct a bunch of it, and we also have to account for like the depth that we're drilling or depth that we're testing. So the good thing is with CPT, it's a little bit straightforward, and I already shared one of them there, but for CPT, we can say ES is usually about 2.5 times QC, where QC is the measured cone tip resistance. So this is the primary thing that we get from our CPT. This is in units of stress already, so it's either in MPa or tons per square foot, TSF. So that's nice because we don't have to normalize by any atmospheric pressure or anything. So we would use this for square footing or circular footing. Or somewhere here, like maybe 3.5 QC or a strip footing, meaning that the length is greater than or equal to about 10 times the base. I think that's, yeah, 10 times the base. So if you have a rectangular footing, then you just use your judgment in between those two functions, right? Like square is that, and you know, you might linear interpolate it or just choose a value in between 2.5 and 3.5 for that. So these are the most common correlations that we use for this. And this is what makes empirical testing nice, is that like these are tests that are performed all the time. Subsurface testing like SPTs and CPTs are performed at any site. So as long as we are matching our empirical relationship to the correct site conditions, then we have a good understanding of some soil properties such as the Young's modulus. So let's look at an example of our buddy Schmertmann's method real quick. So we're told that we have a square footing. That's important to know. It's 3 meters by 3 meters. It's resting on a sand deposit as shown below. And then we are assuming the modulus of elasticity is 2.5 times the cone tip resistance. So we're given the cone tip resistance here, and this is an old school one that's in kilonewtons per square meter, but same thing. Doesn't really matter about the units there. We're asked to find what is the settlement of the footing 5 years after construction. We'll always be given a date because of that creep function there. So either it'll be like, you might say like immediately after construction, which would then you would do like 0.1 of a year or something, or you would give full like 5 years there. So the other things to note that are important here that is given to us is going to be our unit weight of our sand, 17.8 kilonewtons per cubic meter. What else from the site do we see that's important? Do we see a groundwater table? No, there's no groundwater table. So this is kind of nice. So for this, since there's no groundwater table, this means our effective stress is just going to be equal to our total stress. So we don't have to worry about pore water pressure at all. So all of our stresses are going to be effective. We don't have to worry about submerged density, any of that stuff. That makes it nice and easy. The other thing too that we should note is that this is our depth of our footing is 1.5 meters. Our column load or our structural load here is 1500 kilonewtons. And then our area is it's a 3 by 3 square footing. So our area is going to be 3 times 3 or 9 square meters. So let's first calculate the front things of our equation here. So let's first just try to calculate all of this stuff, and then we'll worry about the influence stuff on the next page. So our C1, this is our correction due to stress, and it follows this function. So it's 1 minus 0.5 times the stress or our in-situ stress at our depth of our footing, our stress from our foundation minus the in-situ stress at our footing. So our Q value okay. Our Q value is going to equal our unit weight times the depth of our footing, which is 1.5 meters, times our unit weight, which is 17.8 kilonewtons per cubic meter. So this is going to be 26.7 kilonewtons per square meter or kilopascal. And again, it's effective is equal to total because there's no groundwater table. If there was a groundwater table at the surface or at the surface, then we would have to worry about this. So it's the Q here at this depth. This is our Q. Okay, our Q bar, this is the stress due to our footing. So this is the force of our footing divided by the cross-sectional area of our footing, which is 1500 kilonewtons divided by the area, which is 9 cubic meters, which is equal to 167 kilonewtons per meter squared, or 167 kilopascals. So our C1 is going to equal this. equal about 0.909. That's a 905. Remember, these C1 factors should either be less than 1 by a little bit or greater than 1 by a little bit. So if you're getting like a number in like the 10s or the 20s, then double check your work on it. Okay, hopefully you can see too, these type of problems, ooh, they are Excel. Like if you are an Excel fan, you'd eat it up because it's just a general format and then they're just plugging all these things in. Okay, so the next thing that we need to find. Oh, I guess I didn't calculate the other thing down here. Let's do the other C2 real quick based off of the creep. So our C2, second coefficient, this is 1 plus 0.2 times the log of the years that we care about. So that's 5 years divided by 0.1. This is going to be equal to 1.34. So let's make sure I'm correct. The log of, yeah. So this is what I said, like if you're not given a settlement, if you're saying like immediate, let's say like you're just told immediate after, then use a time of 0.1 year. And if you do that, then that log, it's 0.1 over 0.1, which then becomes 0. So then, or sorry, log of 1 is 0. So then your C2 becomes a coefficient of 1. So it's not changing the equation at all. That's where that 0.1 is coming from. Okay, so we have this whole front matter now. We have our C2 function, we have our C1 function, we have our Q bar, and then we also have our normal, our stress right there. So we have everything out front. So we have those functions. I put them there on the bottom left. So now what we need to do is find our influence. So this second part. So this part of our equation here. This is again where Excel is very helpful. So we have our different layers. We have 1 layer, we have 2 layer, 3 layer, 4 layer, and 5 layer. We know that this is a square footing, so we first need to find our max influence. So the max influence for a square is at a depth of z times 0.5 times the base. So that depth, or that would be at a max influence of 0.5 times the base, which is 1.5. I'm just going to draw this here. So this is where we should expect to see that max. Does that color show up okay? 1.5 meter. So that Z max is going to be 1.5. And then for the square as well, a square footing will go to a max depth of 2 times the base. So 2 times base is 6 meters. So let's see, would that be, so 1, 2.5, 3.5. Okay, so that's 6. So we know that our 6 meters is right here, which is where our max is going to end. So what we have to do is first find this Q1Z. This value here, which is our effective stress or our in situ stress here. So this is going to be our QZ1. I don't know what that one is for, but let's calculate that out now. So QZ1, sorry for the extra parenthesis. So we have 1.5 plus 1.5, which is 3 meters in depth. And then times our unit weight of our soil, which is 17.8 kilonewton per cubic meter. Remember, we have no water table, so we don't have to worry about subtracting out any pore water pressure. So this is equal to 53.4 kilonewton per square meter. Any questions so far? You guys see where this is coming from? It's weird terminology. I don't know why they don't use sigmas like we're used to seeing it. But this Q bar is the terminology they use for it. Okay, so now that we found that value, we have everything that we need to calculate our maximum influence value. So we can plug everything in here. 0.5 plus 0.1. And then this is 167 minus 26.7 all over 53.4. And they're all in the same units, so I just took the units out. But make sure you're plugging this into your calculator, or if you're using Excel to generate this automatically, make sure you're doing it in the correct order. Like take the division, then square root that, then multiply it by 0.1, then multiply or add 0.5. So this max influence value is going to be 0.66. Which again is going to be that peak value that occurs here. So this is that IZ is going to be occurring right there at that depth of 1.5. IZ max. Occurs at that depth. So now we know the starting point of our little profile, our trapezoid profile, because it's a square footing. We're going to have it start at 0.1, and then it's going to go down to a depth of at a depth of 1.5, and it'll have that IZ max value. And then it'll be another straight line all the way down to a depth of 2 meters where it will be 0. And so again, as we're plotting it here over those layers, we have that first point, and we have the second point, and then we have that last point at 6 meters. So that's going to be our profile. So the other one that we found on the last one is that a depth, a Z of 1.5 meters, we have this IZ max of 0.66. Yeah, 0.66. So we overlay this on our layers. So this is why we still have our layers right there, and I just color coordinated them there, but you can, use hatches, or you can just draw lines across them. And these layers, we need to find the midpoint of the IZ value of each of these layers. So we would find that midpoint there at 0.5 and then interpolate on our graph, or if we're using plotting software or if we're using AutoCAD, then you can find it automatically. So we'd find that at that center, the center layer of this one, we would find that there, go up and find our influence factor there. Then third layer, we do the same thing, and so on and so forth. And we would get our corresponding IZ values in the middle for each one of our layers. And that's what we would put in our table there. So that layer one, again, this is at the midpoint. So this value is at that midpoint. The delta sigma z, this is from the delta z, this is just the layering. And then the ES, this is from that correlation here, there. So you can just plug that in Excel based off of that. So when you're adding up these in our equation, remember, you're only doing this for each one of the layers that we have. And it's each one of the layers underneath the footing. So we don't care about anything above it like that we're doing because the depth of footing is going beneath that. So you might have 4 layers or 6 layers above that. We do not include that because the footing is below it and the footing is applying the stress to the soil beneath it. Okay, so last part of this, out of the last one, 3 out of, or should be 3 out of 4, whatever. This should be 4, 3 out, or 4 out of 4. So in Excel, then you would add up each one of these individually, and the units are a little funky, meters cubed per kilonewton. The summation of all of these is 25.48 times 10 to the negative 5. These are going to be small numbers. And then so we can calculate our settlement accordingly now. So our elastic settlement is going to be equal to our 2 coefficients, 0.905 times 1.34, and then times our depth at our foot, or due to our column, or due to the foundation, minus the effective stress at our footing, and then all of this multiplied by thing we just found. And it's important to think about the units when it comes to this. So again, this is going to be, well, these units will be kilonewton per meter squared. This will be meters cubed per kilonewton. So what this is going to equal is kilonewtons per meter squared times meter cubed per kilonewton. So our answer will be in meters. And so we should hopefully expect a small answer here. So SE, our elastic settlement, is going to be 0.04335 meters. This is what Excel will tell us. Do we tell our client this? No, we say expect about 50 millimeters of settlement. Because again, this is an empirical procedure. We can't be that precise. We can't be 6 digits precision. In the real world, we're just going to say it should be about 50 millimeters. All right, any questions on?
You're drawing your lines like on a paper,
Mm-hmm.
why at the depth of 0, like right at the front of the footing, is 0.1?
So that is the starting point, based off of, so that's influence, meaning like it's the value of, or it won't be zero because it's not or because there's load right there. But here, look on this first one right here. So if you have a square footing, it starts at 0.1. If you have a strip footing, it starts at 0.2. Yeah. And you might be thinking, it's like, okay, why is the max value underneath the footing? And that's a good thing to assume. This is assuming that during construction, you might be compacting the soil beneath the footing to start with before you construct your footing. So like when we're talking about natural soil influence, it might be a little bit deeper. Where like obviously like directly under the footing, you're going to feel it the most. So like that's why that shape increases a little bit and then dies down. Okay. So the key takeaways from elastic settlement. And the two things we usually consider with settlement is elastic versus consolidation. So for elastic settlement, it happens, I'm going to say immediately. But obviously there's still creep that is involved. So like what that example we just talked about was like 5 years after. Usually elastic settlement occurs much quicker than consolidation. So it happens immediately compared to consolidation. So with the elastic settlement, to estimate in the field, there's the theoretical technique, which is, bowls, sorry, bowls. And then there's another one too that we didn't go over, but Yan Bu also has one for clays. So there is immediate settlement that can occur in clay. Jambu, he's in Norway where they have a lot of like compressible clays and everything. But it's usually nothing going to be compared to the consolidation settlement in clays. So you might come across that if I don't remember if they asked it on the PE or not, but you might have to like look that up for some reason. In Florida, though, we don't really care for elastic settlement in clay. But there are theoretical techniques for that. And then, of course, we also have the empirical technique, which is our Schmertman that we just showed there. When it comes to consolidation settlement in clays, most of the time, these would all be experimental techniques. So it's neither theoretical or empirical. You're going to be doing consolidation testing and recreating the settlement that you would expect to feel in the site. Now we're starting to dive into a little bit of empirical techniques for consolidation, but still at the end of the day, the tried and true method is the consolidation test to estimate consolidation settlement. So a lot of times elastic settlement, the key thing that is important for this is going to be differential settlement. Often more crucial. Again, like, I mean, in the last example, we said a calculation of 50 millimeters settlement for elastic settlement. Now, most elastic settlement is going to occur during the construction stages or directly on it. So if all of your footings settle 50 meters, or 50 millimeters, If all of them settle, that might not be that big of a deal. It's not going to affect drainage as much. It's not going to affect the structure. But when it comes to differential settlement, let's say like this column settles 100 millimeters and that column settles 20 millimeters, then we have issues because then you can have the drywall cracking, the stresses like that based that are tilted, different types of pipe plumbing issues that could settle. So oftentimes what we're looking for is this differential settlement or max acceptable settlement that's shown by this sigma or this beta. And this is calculated by the change or the deformation by the length. So this would be like if we had so that's like a frame of a structure or something. So we have these length apart and then a change in deformation. So let's say like this side will settle more than the other one. So that net change in deformation. And you can look up, there's a lot of different accepted codes for this, like based off of the material type, like plaster will be able to achieve a certain amount of differential settlement. And it's all shown in these functions, delta by length. So it's like a slope rather than just a set settlement. So yeah, aside from that elastic settlement, a lot of times you are going to be using Schmertmann's. There's software that will calculate that. And the most important part is finding that Young's modulus, making sure you're using the correct Young's modulus. All right, so elastic settlement and just settlement in general, consolidation, settlement, and that can cause issues, right? And like that is obviously different types of settlement, especially differential settlement, will cause soil to fail, which will then cause the structure that we're placing soil to quote unquote fail or not have its intended use. But there's another type of soil failure that we have to design against as well, and that's shear failure. These are a little bit more catastrophic and like our landslides or our bearing capacity failures. Usually this requires the entire scrapping of projects rather than just like underpinning and jacking up a project if we have differential settlement. So these are a little bit more extreme and less common, but still something that is very important to design against. So this has to do with understanding the shear strength of soil. So shear strength of soil is a very important topic. So what we want to think about is the failure in soil often occurs primarily due to the frictional shearing. So since we're dealing with granule material or a bunch of small little constituent parts, then when we push on this structure, what we're looking for is the particles rolling over on top of each other and then pushing the particles out of the way. And a lot of times this failure mechanism follows a progression plane where if we were to apply a force on this, what we would see is that these particles would push here and then push there and then roll this way, and we would develop some type of shear plane. And if you've ever gone to the beach and like, especially on a slopey area or something, you've probably like witnessed this without realizing it, right? You push on it and then a big wedge of that material will slide down. Or if you are, like any other type of failure, like a slope failure, you see this soil moving as a mass. So usually these geotechnical structures are designed, like if we're designing a retaining wall or if we're designing a foundation or a slope, instead of designing for the shear strength in general, we're designing for the shear strength against that specific type of failure. So we're going to talk about different types of failure because a retaining wall is going to fail separately than a foundation. and fail or differently than a slope, as you can see in these cases, different scales, different levels of it. So when we're talking about the strength or the resistance against that, we design these implicit properties. So it's a little tricky compared to steel design or structural design, where you have a general understanding of the mechanics of steel and like the yielding stress and the compressive strength and the tensile strength. And then you apply those properties to steel and then the design. For geotech, we kind of bypass that. We know shear strength as a concept, and instead we develop capacity functions, or we develop the strength against failure for these certain cases, because the failure case is going to be different for each. So the whole basis of this comes from this Moore-Coulomb failure criteria. So there's two names there. I forgot, Robert Moore or something Coulomb, those two guys up there. And Moore may sound familiar from like Moore's circle, like Wade long ago in strength of materials. And this is like a concept of like physics and stress. And then Coulomb took the engineering side of it and the granule mechanics side of it and applied it to our soil. So essentially what we're looking at here is material will fail when the shear stress along this failure plane becomes some unique function of normal stress. So this is the physics side of it. Essentially what we're saying is that if we have this, let's just say this plane or this frictional surface, the shear stress is the resistance to roll down this surface. And as we change the normal stress, this shear stress is going to change as well. And this is something from physics, right? That we've talked about in Geotech 1 and everything failing. Like think of a piece or just pushing a box on carpet. Like the heavier that box is, the harder it is to push it on the carpet because the increase of that friction. So we see the same thing with soil, is as we increase the normal force, the more that friction increases and the greater the shear strength is. So what we see is that the shear strength of soil, so shear strength is the capacity. We're going to recognize this as the shear stress at failure. This is a function of our normal stress, which we've been talking about is our sigma value. So this is one of the most confusing parts, is that the shear stress at failure is considered the material's shear strength. Right? Like kind of a way of like thinking about it too, like working out or like running or something. Like usually you define your strength as something that is like the max capacity that you can do. I can bench whatever, 20 pounds or something, probably more than that, hopefully. But you know, that's how you define your strength, by the max capacity. So that's kind of the term. A lot of times it can get confusing hearing shear stress all the time and then shear strength, but just remember that that's what that means there. So this shear strength, again, which we show as this, well, I guess we show both of these as this tau. Tau is how we represent shear. It depends on three things in soil. So it depends on the frictional resistance, and thinking about like grains and stuff, like what type of frictional resist, like what might play a role into the frictional resistance, like thinking about like sand or soil or something. Yeah, somewhat unit weight. Or like think about like if you zoom in on sand particles, like what might cause that sand particle to have more frictional resistance if that sand was shaped differently, if it was angular or so, like rounded, you know, like if it had a bunch of little marbles, that might have a little bit lower of a frictional resistance. So like from a material property, we're talking about like angularity or like the flakiness, if you remember back from aggregate, we were talking about that. So that's going to be a big thing, the frictional resistance. The other one, which is more so what you were thinking, Chris, it would be the interlocking forces. So this is like our density or a normal force or a void ratio, like how much these are packed in together, how much the soil is packed in together. So yeah, this is usually density. Frictional resistance would be like angularity. Do we have a nice round particle versus a, you know, frictional particle, something like that. And then the last one too would be the electrostatic bonds or just bonds in general, which really is only applicable to our clay because remember, clay is cohesive. Remember back from geotech, the main properties of clay is the particles are so small that they're highly influenced by water. So those particles actually stick together due to electrostatic forces, which we call cohesion, which makes it plastic. And that's why you can take clay and it can stand up on itself and retain its shape, where sand, if you try to retain its shape, it's just going to fall apart. So these three things are the things that control the shear strength. And it's always important, like we'll show all these tests to help us calculate the shear strength and everything and all these laboratory experiments. But keep this in mind when when you're looking at the numbers. Like generally, if a soil is more dense, then it's going to have a higher interlocking force. So we're going to have a higher density, which means we should have some high strength. If we have high frictional resistance, meaning it's very angular, like it's, you know, the rock is angular itself, then it should have. And obviously, if we have more cohesion in our clay, then it should have a higher strength as well. So the way we find this is through a Moore Coulomb criteria, because remember, the shear stress at failure or the shear strength is a function of our normal stress. So what we're going to plot here is our normal stress versus our shear stress. And essentially what we see is if we have these points of failure, we're going to have this shear failure at this level will correspond to a normal stress failure at this level. And then let's say we have an increase of shear stress. Oops, that's a sigma. So on and so forth here. Where as we increase our normal stress or we increase those interlocking forces, then we will see an increase in our shear strength. So the cool thing is that if we were to actually do this out and plot them, and pardon, I hope it's actually going to be this way. It might not be because I'm not, just kind of winged it. But we will see it follows a linear function. And this linear function can extend out, you know, for ever there. And so this is called the Moore Coulomb failure envelope. envelope. Which is kind of cool because essentially what we're saying is if we have any combination of normal force and shear force in our soil below this level, then we are safe. There's no failure. So this failure is represented by the function or by that envelope. Up here, if we have it above, technically it's impossible because the soil's already failed. So this is a linear relationship, which is good because we can set a function to this linear relationship. So what we can do if we know that failure is a function of this, how we would actually set this function. Well, first let's define it. What would we need to know? We'd first need to know the slope of this function. If we wanted to create a linear function, remember y equals mx plus b. That'd be the line there. So we need the slope. What we call this slope is this phi. This is shown in angles. This is called our friction angle. And then the only other thing that we care about is the potential intercept. So sometimes there is no intercept and it's equal to 0. But if there is, we call it this C function. Now think about what that is telling us. If we have a shear strength when there is no normal force applied to it. So if we have a y-intercept here, like at this, we have a shear strength with no function applied to it. What would that be? That would be our cohesion. So all that to say, if we were to define this function, and we'll catch up with this after on class on Monday, this is how we would define it. So the cohesion plus our slope times our that would be the Moore Coulomb failure criteria. We got to head out. So this is where we'll stop. We'll start back on this slide on Monday. So give me just about 30 minutes to make sure the quiz is okay. And I will post that quiz. And don't forget your homework is due on